board before we start. Okay, so for the first, not the first example, but from continuing from the last class, we're doing 8.3. It's still the 8.3 section, okay? But we're going to continue from example 10. And I cannot remember what problem it is like in the WebAssign, but the last 4 problems should be exactly like these last 4 examples, okay? The only thing that's going to change is these numbers that they give you, okay? So it says, find the angle between the forces given the magnitude of their result. And then it has a hint. It says, write force 1 as a vector in the direction of the positive x-axis and force 2 as a vector at an angle of theta with the positive x-axis, okay? What does that mean? So it means for the first one, you're going to want to have that vector on top of the x-axis just like this. So if you're figuring out what its coordinates are, it's gonna have some kind of x coordinate, but it is not gonna have a y coordinate right there. If my terminal point is on top of the x-axis, there is no y value, right? That y value there is 0, okay? But for 2, it's telling me that that one's gonna have some kind of angle from the x-axis. So all it's saying is that your angle is here, okay? We don't know what that angle is. We just know that we're gonna use theta, and that's it, okay? What we do know is that if force 1 is this, I'm gonna go ahead and call this little vector u, and then call this one v, just to keep them different, right? To separate them, so we know which one we're talking about. And so for u, we know that the force is 3,000 pounds, which means that its magnitude is going to be 3,000 pounds. We also know that the force for the second one is going to be 1,000 pounds. So that means that this guy's magnitude is going to be 1,000 pounds. Okay, so then if I want to write the vector for u, I can write the vector for u because I know what the angle is here, right? If I'm thinking about the angle for like this one, if you're thinking about the angle from the x-axis, what is the angle when you're right here? It's 0 degrees, right? The angle right there is always 0 degrees. This one I don't know, but that one I know for sure is at 0 degrees, okay? So when we're writing our vector, it's going to be the magnitude, cosine of that angle, comma, magnitude, and then sine of that angle. For the v vector, it's going to be the magnitude, which is 1,000, and then cosine of this angle, which I don't know, right? And then the magnitude again times the sine of that angle. Again, I don't know that angle just yet, okay? That's what they're asking me to find, right? Literally says find the theta, right? So that's the guy we're trying to figure out. But I do know something here. I know that the cosine of 0 is 1. So 3,000 times 1 is just 3,000, right? And I know that the sine of 0 is 0, and 3,000 times 0 is just 0. So it fits what I was talking about before. Didn't I mention that, right? If this is what your vector looks like, it's going to have an x coordinate, but no y coordinate, right? And that's exactly what we found. We just now know what that x coordinate is, okay? Now, they also give us another extra bit of information. They tell me that the magnitude of the resultant force, resultant means when you add them together. So the magnitude of the resultant force is 3,700 pounds. Well, what would that look like if I actually added these guys together? That would mean that I'm taking this and I'm adding it to this. And how do you add vectors? You add their components, right? So I would be taking the 3,000 plus this, getting 3,000 plus 1,000 cosine theta, and then 0 plus this one, which is just 1,000 sine of theta. And if you're trying to find magnitude, you're taking the square root of each component squared. So this guy squared, and then this guy squared. Oops. Now I'm gonna scoot my paper over because this is gonna be very big numbers, right? Now all of these things is still 3,700 on this side of the equation, okay? So I'm gonna scoot that over here just so I can fit everything in this radical, okay? Because I am squaring, this one's not so bad. I'm just squaring one term, right? But there's a big plus sign in the middle here. So I'm actually squaring two terms over here on this one, which means I have to FOIL it out, right? I have to have one of them times the other and then FOIL them out. So it's gonna be 3,000 times 3,000, which is 9 and 6 zeros. Then it's 3,000 times this term, which is 3 and 6 zeros, cosine theta. Then I'm gonna do the other one, which is 1,000 times that. Again, you get that same 3 with the 6 zeros and cosine theta. And then finally you get this guy times himself. So you get 1 with 6 zeros, cosine squared theta. And I'm not able to squeeze in that last term, but the last term would be this guy squared, which is 1 with 6 zeros and then sine squared. Okay, I tried to squeeze it on there, but it's too long. So remember, all 4 of these terms came from FOILing this out, and then the last term came from squaring this guy. Okay. This is all just mechanics from here, really. So let's see, 9, 1, 2, 3, 1, 2, 3. I have these guys, they are like terms. Both of them have a cosine, right? And so since I have 3, however many that is, 3 million plus 3 more million, that means I'm gonna have 6 million cosine thetas. And then I still have the cosine squared term, and I still have the sine squared term. Now here's where it gets a little bit interesting. 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. I'm gonna factor out that million. When I factor the million out from these two guys, I have just cosine squared plus sine squared inside here. What is cosine squared plus sine squared? Just 1. So really I can combine this constant and this constant, which gives me 10 million. So now there's 7 zeros. And I still have this 37 over here on this side that I never did anything with. Okay, it's just still there. But my job is to solve for theta. So what would be my next step? Now that this doesn't look so large anymore, I mean, it's still got these big numbers, right? But it doesn't look as complicated as it did earlier. What would be my next step to try to get theta by itself? If you're still copying, keep copying. I'll wait. It's a lot of zeros all over the place. Yes.
It's only because I want to point, but you have 7 zeros in the first 9.
On this one? Okay, 1, 2, 3, 4, 5, 6. Yes, yes. Thank you. Okay. Everything counts because the stuff has to be perfect, right? Once I upload it. Can I just minus the 10,000 and divide by the 6,000 or 6 million? Can I just do that, or do I have to do something first? I have to get rid of that house, right? How do you get rid of the house? What's the opposite of a square root? A square exponent, right? But if I square that side, I have to this side. And I do not know what that big number is going to be, but go ahead.
You have to square the 37.
Mm-hmm.
I mean, square root it.
Not square root it, square it. Because this will get rid of the house. The 2 power gets rid of the 2 root. So if I apply a 2 power to this side, I have to apply a 2 power to that side. Up here? No, the magnitude is 3,700. And I'm just trying to find what that magnitude looks like as an expression. So I was finding the magnitude of u plus v. It's really like this. If this helps at all. It's really 3,700 equals the magnitude of u plus v. And then I'm going and trying to figure out, this is u, this is v. I plugged in u, I plugged in v, and then I'm simplifying.
Okay, it's not square root it, right? Or was it that one point?
No, that's the definition of a magnitude. Oh, the definition of a magnitude is to take the square root of each term individually. So I didn't put that in there. It was there for as part of the rule. Yeah. Good question. Good question. Yeah, you got to see everything, right? Okay, I don't know what that number is though. When I square, it's gonna be some huge, ugly, weird thing. I get 1, 3, 6, 9, 1, 2, 3, 4. And then my 10 million, and then my 6 million cosine theta. But now the right-hand side doesn't have the little house on it anymore, right? So now I can minus my 10 million. 1, 2, 3, 1, 2, 3, and an extra. So 1, 2, 3, 1, 2, 3, and an extra. Oh, wow. I'm gonna have to go over to the next page. Oh, shoot, I don't have room. Of course. So I'm gonna use another page then and kind of put it in when I upload, okay? So when I subtract the 10 million over here, I'm gonna get 3, 6, 9, 1, 2, 3, 4. And when I do it on the right-hand side, I'm just gonna get the 6 million and then cosine of theta. What would be the next step to try to solve for theta? Divide by 6 million. So I get that big number minus 10, 1, 2, 3, 1, 2, 3. So I take that, divide it by 6, 1, 2, 3, 1, 2, 3. I get this decimal in my calculator. And those just wipe out. But then how do I solve for theta? In order to get theta, I'm gonna have to do the arc cosine or cosine inverse of this number. Let's see what that is. I have degrees in my calculator, so I get about 52 point. This is what I get in the calculator. And depending on what the computer wants you to round it to, it says it wants me to round it to 1 decimal place on my, at the very beginning of the problem. So then mine's gonna round to just 52.0 degrees because the 4 is not enough to make the 0 go to 1, right? So this would be my answer for that problem. why I thought I could squeeze all that in that little spot. I needed just a little bit more paper to finish it. Now, sometimes you might get smaller numbers, like they might be in the hundreds, and so there might not be so many zeros, but most chances are, if you're doing this problem in WebAssign, it's gonna have all these zeros in it, okay? Don't let the zeros distract you from what's going on, okay? Yes,
What did you do in that step? Blue.
right here.
Yeah, which blue not or above that?
This was gonna turn into a 1. So then 1 million times 1 is just 1 million, right? So this is gonna be a constant of 1 million plus this constant of 9 million is where I got the 10 million from.
Oh, it's just one.
Just combining those like terms, yeah. So these two guys made the 10 million. Okay. I could have written a whole nother line in there, right? But I didn't.
I thought it was 90,000, so it's like-
Oh, yeah, yeah. Yes, you have to be very careful with the zeros. You do. Go slow, don't rush through it, okay? Okay, let's look at the next one because they're all like the ones in our homework. It'll definitely help us when we go to try to do that homework. Okay, so this one is a different kind of problem. It's not talking about pounds, it's talking about newtons, but for the most part, we're still gonna kind of follow the same process, okay? So it says forces with magnitudes of U equaling this. Now it's telling you that the magnitude of U equals this. So that actually means the magnitude of U is the 2200 newtons, okay? Then it says, and the magnitudes of V is going to be 750 newtons, okay? It used it in words, but I'm just putting it in symbols, okay? So it did tell you that those magnitudes were this and this respectively, okay? And the angles for each one is respective. So they give you this image here and they're telling you that for the U, you know that the magnitude, so you know that this length is 2200 newtons, and you know that the angle is 30 degrees from the positive x-axis. For V, we know that this length or this magnitude is 750 newtons, which is why it looks shorter than the other one, right? Probably not proportionate, right? Because if I multiply this by 3, I'll probably get something close to that, right? So this one should be 3 times shorter than this, but it's not, right? They don't look like that. So they're not to scale, obviously, okay? But the figure can still help us figure out what's going on. It wants us to find the direction and the magnitude of the resultant forces. So if I want to know the direction and the magnitude, that means I need to know the theta and the magnitude of U plus V. That's what they're asking me to find, okay? They're asking me to find theta of U plus V, and they're asking me to find the magnitude of U plus V, okay? Well, in order to do that, I'm gonna have to add U and V. And in order to add U and V, I'm gonna need to know what the heck U and V look like, right? So U is going to look like its magnitude times the cosine of that angle used to locate it. And then its magnitude again times the sine of that angle. And then I'm not sure what these values are, but I'm going to type them in my calculator. So I am in degree mode. 2200. Oh no, this calculator goes backwards. Times 2200. So I get this decimal, 190.1905. Double check in your calculator that you get the same value as me. I want to make sure that I'm not doing this wrong in here. And then sine of 30 times 2200 will just be 1100. Make sure you get those same two values. I'm just typing this in the calculator and this in the calculator. So for V, it's going to be very, very similar, except I have to use his magnitude and his angle. So it's going to be 750 for the magnitude, and then cosine of that negative 45 degrees. And then the magnitude again, sine of negative 45 degrees. I'm just going to plug those in my calculator and see what I get. So 45 negative and cosine of that times 750. And then 45 negative sine of that times 750. I get negative. And I always like to double check to make sure that everything looks right. If this is my positive x-axis and this is my y-axis, this terminal point right here, shouldn't it be positive x and positive y because of where it's located? And I did get positives for u, okay? But if you look at V, it has a positive x, but it has a negative y value, doesn't it? Okay, and that's exactly what we ended up with here. I just like to confirm that just before I keep going to make sure I'm good to go before I keep on, okay? From there, we need to talk about this resultant, okay? So we need to figure out what the resultant is. Before you do the magnitude, I'm just gonna do U plus V. So to do U plus V, I'm basically going to take the first component of U and add it to the first component of V. That's the definition of how you add two vectors. Then for the second components, I'm going to take the second component of U and add it to the second component of V. So it's not that this stuff is like super complicated. It's all these decimals and numbers that you got to keep track of. Okay. Let's see, what do we get? 1905.888 plus 530.3300859. But if you'd round too soon, it's chances you'll get the wrong answer. So that's why I'm just writing all the decimals I get. And so I have this for U and V. So we need to recall our formulas. For the magnitude of U plus V, all we have to do is take the square root of each component squared. So this guy squared and then the other guy squared. Now I'm writing down every single step because in case somebody's coming back and watching this. But if you just write what it is you get when you square them, that's okay too. Kind of save yourself a little bit of writing. For me, I'm not even going to bother. I'm just going to type all of that in my calculator. I'm not bringing the right calculator, but it's okay. So 5.58974 squared plus 569.6699 squared equals, and then take the square root of that. So this is what I get when I do that whole thing, the square root and everything in my calculator. And it's asked to round to one decimal place. So this would be 2501.3. And since the other magnitudes were in newtons, this magnitude is going to be in newtons also. Now, in order for me to find theta for this resultant vector, that is going to be the tangent inverse of the x component, sorry, it's always sine over, right, y over x. So the y component over the x component. So in this case, that would be the 5, 6, 9.6, all of that over the 2, 4, 3, 5. Okay, and I don't know what I'm gonna get, but I do have my calculator in decimal mode, so let's see. And 10 inverse, oh, no. I think you get 13 degrees, but let me make sure real quick, because I think I typed it in there wrong. 2, 4, 3, 5.58, 5974, and then take the 10 inverse. Yeah, you do. You get 13.1645053 degrees, which to one decimal place is 13.2 degrees. If you round at any point before the very end, you're going to be off. And then the computer is going to keep counting you wrong. Okay. That's why I've been writing down all the decimals that my calculator shows every single time. Okay. Because you don't want to round too soon. If you round too soon, you might get 13.1 and then it's going to tell you you're wrong. Okay. Or you might get 13.3 and it'll tell you you're wrong. Okay. Just because it's off by a little bit. So I know it's annoying to write all those digits, right? But we want to make sure that we get the correct solutions, okay? Okay, so not too bad so far. I think the next one, oh God, the next one's the worst one. Oh yeah, the next one's the worst one. This is the one where it's really long, really long. I'm so sorry, but we have to do it. Especially if you guys are going to be engineers, like we have to do it. Okay. It's torture, but you want to be an engineer and that's torture itself. So, so that's your life from now on, to be tortured by science and mathematics. Okay. So for example 12, this one I am going to try my hardest to like break it down and explain it so that you can see all the pieces and where they all go, okay? I had to like do it 10 million times so I can figure out how am I gonna explain this? Because when I looked at the solution, there's a video to this problem and the dude was just like, oh, it's this and then it's this. And I'm like, what? Where did that come from? And how in the heck does that give you the second step? Like, I did not understand that video at all. And I know if I can't understand it, then I'm pretty sure the students that are just now learning it are not gonna get it, okay? So I'm trying my hardest. It's gonna take me a lot of paper. I gave myself some extra room on the next page because it's just gonna be a long one, okay? I'm trying. I have my notes here to try to help me to make this really clear, okay? So the problem says, use the figure to determine the tension in each cable supporting this load here. So this is what they're carrying, okay? And it's want me to round it to one decimal. And it says hint, do not round. This is my hint, by the way. It doesn't say that in WebAssign, okay? This is just me telling you. Do not round any steps, only round your final answers, okay? I know it's annoying to write all those digits, but I promise this one I did it by rounding it and then I got it wrong, even though I was off by like just a tiny smidget, okay? So make sure that you don't round until the very end. Okay, here goes. One thing you need to know is that the tension of this cable here, okay? To identify this cable here, I'm gonna use the vector AC. So I'm going from A toward C. So the tension from that vector, okay, is found by taking the magnitude of that vector. Now, for just so I don't have to keep writing AC, 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 AC everywhere, okay, I'm going to call this vector U. Okay, so then that means I'm only needing to find the magnitude of U. Now, I also have to do the tension of this cable. And the tension, I did not spell that right. The tension of this cable, remember the wire's being pulled down this way, right? So the tension of BC is going to be the magnitude of BC. And again, just for simplicity purposes, we're going to call this vector V. So I don't have to keep writing AC and BC all over the place. Okay, I can just write U and V. Now here's where it gets a little funny. Okay, the coordinates for this, it's gonna get real weird, okay? The best way I could explain this to myself was if I took this spot right here and I put an axis on it, like my X and Y axes, okay? And then I took the other spot and put another X and Y axes. I'm gonna do them in 2 different colors to help sort this out in our brains. Okay, so when I'm talking about U, I'm gonna be using this pink color, and when I talk about V, I'm gonna be using the blue one. Okay, just so that we can keep them separate here. Okay, now I can tell you what the coordinates of this U is. I know it is because notice that it's going to be going across this way. How many inches does it go this way? In order for me to get here, I've got to go across this much, and then I got to go down that much, right? And what is this distance here? How many inches? 10. And then I got to go downward so that I get right here. But how far down did I go? 24 inches. Now I'm going to do the same thing with V, but not yet, okay? I want to finish up with U. Now, I also know that we've got this angle here, and I'm going to call it theta for U, because we're going to have a lot of thetas, and I don't want them to get confused, okay? So that's theta for U, okay? If I want to find that reference angle, we're going to use the same formula that we did on the other page. We're going to do the tan inverse of the y component over the x component. I made an error. Did I go up? If I'm down here in this quadrant here, the y value is supposed to be negative, isn't it? So this should have been a negative 24 because I'm down here in the negative zone. So when I do my y coordinate, it's going to be negative 24 over my x coordinate, which is 10. Now, when I do that, this is the reference angle. This is not actually what theta is. It's just the reference of theta u, okay? The reference angle. So I should not write that. I'm just going to leave it alone. I'll explain in a second. I'm not going to label that guy, okay? When I type this in my calculator, let's see what I get. 24 negative divided by 10 is 2.4 negative. And then I'm going to take the tan inverse of that. I get negative 67.38. I get a whole bunch of decimals. I'm just going to go like this. Okay, but that's how many degrees I get. That makes sense, right? If I'm going below this, I'm going in this direction, it would be a negative angle, right? So I know that this angle is negative 67.3801, so on and so forth. But that's not what theta u actually is. theta u is how long does it take if I go clockwise to come all the way around till I get to this vector, okay? That's the actual theta u. And that angle is not gonna be a negative angle because I'm going clockwise. So if I wanna find theta u, the actual theta u, I have to take this reference angle and I have to add 360 degrees. When I do that, I get 292.6199 degrees. Now that makes sense, right? I'm past 180, I'm past 270, and I'm at 292 degrees about, right? That makes sense for the location of where this vector is, okay? So I have found that theta. So then now I know that u is going to be the magnitude of u, which I don't know yet. That's what I'm trying to figure out, times the cosine of this angle. And then the magnitude of u again times the sine of this angle. That is another way to write u that will incorporate the magnitude. And I want that magnitude in there because that's what I'm trying to solve for. I want to know what the magnitude is. I need to figure out what the magnitude of u is to give them that answer, and I need to know what the magnitude of v is to give them the tension for the other rope. Okay, so I'm going to pause on all the u stuff, and we're going to do the same thing again, but for the v. Okay, so for the v vector, what are his coordinates going to look like? Remember, this is a whole new axis. Okay, so I'm going in the negative direction for x, aren't I? And how far am I going in the negative direction for x? 20 units. So it's going to be negative 20 for x. And then I also have to go downward, which means I'm going to have a negative y value. How far down did this guy go? 24. So it went negative 24. So if I want to find the reference angle for theta v, I will do the tan inverse of the y coordinate over the x coordinate. And I don't know what that is. 24 negative divided by 20 negative, and then the tan inverse of that. I get about 50.1944 degrees. As long as you round those degrees to 4 places, you should be okay. I did it over and over trying to figure out how many decimal places did I have to go before it would give me the wrong answer. If you only chop it off at 3, you'll get the wrong answer. So make sure you put at least 4, okay, for your angles. Now, that's great. That's the reference angle. That only tells me this angle. It tells me this angle right here. But I know that is not the actual angle because I need to start over here and then get all the way to the vector. So how can I find the actual angle for the theta of v? I don't think I'm going to add 360 this time. What am I going to add? I'm looking right here. This is the number I found. I found out that that angle is about 50 degrees. But I want to know from the x-axis all the way to the vector. 180, exactly, because I have to go this measurement first and then the 50 degrees, right? And this measurement up top, the first 2 quadrants, is 180 degrees. Good.
So it always has to go clockwise.
It always has to go clockwise, and it has to keep going until you land on that vector. So over here, we had to go past the 180 and all the way over there. It really was the same measurement as this reference angle. It's just I couldn't have the negative version of it. I had to get it to be positive. And so it's very important because if you don't add the 360 for the left side and add the 180 for the right side, you'll get the wrong stuff. Okay, so make sure when you're doing the left one, the left, I guess the U is what I called it, make sure you're adding 360. And when you're doing the V, make sure you're only adding 180. Okay. What do I get? I get plus 180. I get 230.1944 degrees. And that makes sense for where it's at, right? Because I'm more than 180, but I'm not quite at 270 yet. Okay, so it does put me right here in this quadrant. So then I can write the V vector with magnitudes. So the V vector would be the magnitude of V times the cosine of this angle. And then the magnitude again times sine of that same angle. And that's how I can write the vector for V. So now I have something in terms of magnitudes for U and magnitudes for V. Now here's where it gets weird. I don't have another color. Dang it. This vector here, I have a red pen over here. I'm gonna use this red pen. This vector here is the resultant vector. It's just gonna go, the weight is gonna pull straight down, okay? So what that means is that my U plus V part, the magnitude, not the magnitude of that, but its coordinates are, remember, if this is the center now, because I'm here now, pretend there's another axis here. Do I have an X coordinate if I'm just going straight downward? No, it's just going to be 0. But I am going to have a Y coordinate of this distance, which is what? But they don't say that. Oh God, how am I going to explain that? Okay, this is how I'm going to explain it. It's telling me that the work is 5,500 pounds. Okay, now the work is the magnitude of U plus V. Okay, now U plus V has got these coordinates, right? This X coordinate and this Y coordinate. Okay, now based on the position, I know that the X coordinate is going to be 0. And it looks like it should be 24, but it's actually not, because doesn't it go even further than that? Right? That rope goes further down all the way to the weight. Okay, so how the heck do I know what it's going to be, right? So I don't know what this is. I don't know what this Y coordinate is. However, I do know how to calculate the magnitude. When you calculate the magnitude, you take the square root of the first coordinate squared and the second coordinate squared. And you get this 5,500 supposedly. So then when I square both sides, I get that Y squared would equal this thing squared. And then if I take the square root on both sides, I get Y equals plus or minus this 5,500. Now here's $1 million question. Is it positive 5,500 or is it negative 5,500? Look at the direction compared to your axes over here. I'm going below the x-axis, aren't I? Here's my x-axis and here's the y-axis. I'm actually below the x-axis, right? And I'm going all the way down here actually, okay? And so if I'm going all the way down there, I'm actually gonna choose y equal to negative 550, okay?
Is that in pounds or?
This is in pound. Well, no, this is just the position. Okay. Up here it is in pounds. When I was doing work, this is pounds. Magnitude is pounds. Once I squared, it's pound squares. But yeah, it is pounds still.
Negative pound?
Mm-hmm. Is your weight, because negative compensates for the direction. Okay. So then now we have this coordinate here that's going to be negative 550. And I'm going to write a little note. Please see other sheet or explanation. Because I explained it over here, right? So I'm going to put that in there when I upload it. Okay. I could find UV old school though. So if I find UV old school, then I basically find this relationship, that this vector should be equivalent to this vector. Now bear with me, I have to write all of this out and it's going to take a lot of space. So first component of the U vector plus the first component of the V vector. And then for the second component, I'm going to add the two second components together. So the second component up there in pink plus the second component in blue. And I'm trying to squeeze it in there. I also have to close up my little vector with those V things. I think I'm going to scoot this over just to fit it all in. So close that parentheses and then close up my vector. So I only have two terms inside my vector, right? The first component, which is this big ugly thing, and then the second component, which is this other big ugly thing. So if I create a system, the only way that this vector can equal that vector is if this first component is the same as that first component, and the second component is the same as this second component. That's the only way they can be equal, okay? So then that creates a system of equations, and it's an ugly looking one, unfortunately. But I'll clean it up and make it look nicer so that it's more, you can comprehend it a little bit better. And then the negative 550 will have to equal the one with the signs. So you've got this system of equations. And so we have to solve the system of equations. Now there's two ways to solve. There is substitution and then there is elimination. I've always favored elimination, and I think elimination would probably be the less messy one. Because if I try to solve for one of these, either the magnitude of U or the magnitude of V, it's just gonna look really, really ugly, okay? So I'm instead gonna actually just figure out what these decimals are. So I'm gonna go figure out this number. 292, glasses are fogging up, 292.6199, and I'm gonna take the cosine. I get 0.384615949, and that's gonna get multiplied by that magnitude of U. Then I'm gonna figure out what this value is. Cosine of that. and I don't get a plus, I get a negative. And that's going to still be multiplied by the magnitude of V. Okay, so I'm just getting the decimal numbers. I'm going to keep this guy the same. And then I'm going to find this value. And so I get negative 0.923 times the magnitude of U plus, and I'm going to find this value. So it's not the process here that's any complicated. It's just all these numbers. Okay, now I have to have the game plan. Okay, the game plan is to always make the numbers match, but the signs have to be the opposite. Okay, now I already have opposite signs for the U's, so I'm probably going to try to eliminate these U's. In order to do that, I'm going to have to make this number and this number the same. So how do I do that? I'm going to take this bottom coefficient. I'm just going to abbreviate, and I'm going to multiply that by equation 1. And then I'm going to take this other number, this 0.384 number, and I'm going to multiply that by equation 2. And I want to add those two results together. Okay, so I'm going to put this here. So if I take equation 1 and I multiply this, this, and this, all three terms of this equation by this decimal right here. Not the negative, because I don't want to change the signs, right? I want to keep this one positive and I want to keep this one negative. Okay, but I'm going to use that decimal and multiply it by 0. It's going to stay 0. But when I multiply it by that, let's see, 0.923076688 times 0.384615949. I end up with this decimal. And then it's still multiplied by the magnitude of U. And then I got to take that 0.923 number and multiply it by this guy. I get a negative. I get a negative 0.59. But I'm still multiplied by the magnitude of V. I just can't squeeze it in there. Okay. Now for the second equation, I'm going to multiply the 550, this number, and this number, all of them, by the 0.38 number. All the digits are right there. I just abbreviated it. Okay. So let's see. 5,500 times 0.384615949. I get a negative 2115. Well, let me skip that over. And then now when I multiply this times the number, I should get the negative of this, but let me make sure. So 0.923076688 times 0.3846. Yes, I do get that same number, but I get the negative. And then now I'm going to take the same 0.3 number and multiply it by this. I am going to get a negative. A positive times a negative will give me a negative. So 0.768222095 times 384615949. I get 0.295470003. Still again multiplied by the magnitude of V. Now when I add these together, what do I get? Okay, 0 and this gives me the same number. A positive of this and then a negative of that will cancel each other out, right? And then these two I can actually add together or combine. I will get a negative 0.590653 plus I get this times the magnitude of V. So then how do I take that and how do I solve for the magnitude of V? It's just a number in front that's multiplied, right? So if I want to get rid of that number in the front, you just have to divide by that number. But you got to do it on both sides. And so I'm going to flip the page in a second. If I divide, I get 2386.467291 and the magnitude of V all by itself. Okay, and it does tell me to this, remember, is the tension of B to C. Okay, so I already know what that is, and if I round it to 2 decimal places, it's 2386.5. Okay, so I have one of those solutions. However, I need to also find U, and I canceled out U, right? But once you get one of your solutions in your system, you can just plug that solution in to either equation to go figure out the other one. Okay, so what I'm going to do is I'm going to take, I think I want to take the vector that had the 0 or the equation that had the 0, and I'm going to plug the answer I got for V right here. Okay, so bear with me. I've got to somehow write this over here. Do I have the same numbers? 0, 3, and negative. Yes, I do. Okay, good. That way I don't have to keep flipping back and forth. So I'm going to plug this magnitude that I just found into equation 1. And this is what I get. I get 0 equals, oh, no, that's not what I get. It's the 8 number. 3846, this ugly number, times the magnitude of U minus this decimal and I got to plug in the magnitude of V. Now, when you plug it in, make sure you use the unrounded number, okay? But that's the number that's going to go in there. And what do I get when I do this number times that number? I have no idea. 0.6401 times this big 2000 number. I get this number. And then how do you solve that for U, the magnitude of U? What would I have to do first? If it were this, what would you do? If this were the equation, how would you solve that equation? you would add this constant over, right? And then divide by whatever was in front of you. So it's the same thing. I'm gonna add that number, that ugly number. And so basically I get the positive version of it over here. And then the last step you need to do is just to divide by this weird coefficient, right? So I divide both sides by that 0.384 number. I'm getting lazy with writing it. So I'm putting the dot, dot, dots. But when I type it in my calculator, I'm using the full long version, okay? So let me see, I have that number in my calculator already, and I'm gonna use the long decimal. And I get 3972.222313. So then that means that this guy, which is the tension between A and C, is about, to one decimal place, it's just going to be 3972.2. Okay. And since tension is basically a magnitude, it is going to be in those, what was it? Was it newtons or pounds when they gave it to me? It was in pounds, right? 3W pounds. So these are both pounds. Not that problem, no, it's too long. It's in the homework, but it's not gonna be on the test. It's way too long. It would take the whole time. I remember this problem too from when I was taking pre-calc. I hated it. Took so long, but then I got super excited when I got it right. So I don't know. Okay, last one, and this one seems like super easy compared to the last one. Okay, so this one has a force of F pounds is required to pull an object weighing W pounds up a ramp inclined at theta degrees from the horizontal. So what I do is I always draw my little axes just so I can figure out what they're talking about. So I am on an incline, and if I draw that incline like this, right? This is the theta of my incline. And what does it tell me that incline is? It says it is 10 degrees, right? So then this angle is going to be my 10 degrees. My W is always going to be this magnitude here to get there, okay? So this is 170 pounds, that magnitude. Magnitude is the same as length, okay? And I can, the question is though, is it says F is the pounds required to pull an object. So I want to know really, what is this measurement here? This is F, okay? I want to know that measurement there. What it's going to take to pull it up. How much force do I have to take pulling it up to get it across that incline, okay? And of course I can round to one decimal place. Isn't this a right triangle? And can't you just use the old school stuff to find that length, right? So I'm gonna use the opposite side over the hypotenuse. And the opposite is F, and the hypotenuse is 170. Should be the sine of that angle, right? And so then if I just multiply both sides by 170, F is apparently that measure, whatever that is. What is that? Let's see. 10 degrees, sine of 10 degrees times 170. I get 29.520, all of this mess. But if I round it to one decimal place, I get 25.9 pounds.
Does it matter that you put it in the first quadrant?
I did that because it said that it was this many degrees from the horizontal. So this is the horizontal, and it's got to be 10 degrees, positive 10 degrees from there. That's why I put it in the first quadrant. If this had said like, I don't know, 80 degrees, right? Then I would have been, well, I still would have been if it was 80, but if maybe it was 100, I would have been over here. Okay. And then I would have had a totally different triangle, right? A different right triangle if it were in this quadrant. Okay. That was like so nice and short compared to that nightmare of a problem, the other one. Okay, so we are gonna move into, this one's the most difficult problem just because the beginning of it is super easy because it's just like, oh, here's what a vector is, but then they just go jump into like turbo mode and give us all these hard, complicated word problems, okay? But we are gonna go back a little bit and go to something in the next section, which is a little bit on the lighter side, okay? So although I have to introduce you to that one problem with the tensions of the ropes, so when you see it in physics, when you take they call it university physics. They have it here, even though we're not a university. But when you take that level of physics, that's after you've had calculus, you're going to see that problem again, okay? You know how to solve it the pre-cal way. I don't know if there's another way to solve it once you learn calculus, okay? I never revisited that problem, so I don't remember, okay? But I think it does come up again in your physics class. I think it's the same thing, because when I remember taking physics, I think we used pre-cal the same. So it's the same problem. Okay, 8.4 is vectors and dot products. So this one's gonna be more mechanical work, okay? So if you were great at algebra, you should be okay in this section because it's just computation, that's it, okay? There's nothing really crazy happening in this section. So there are two different kinds of products. We don't talk about both of them in this class. When you get to Cal 2, the entire first chapter is going to be vectors. So you're going to see all the stuff that you saw in this whole chapter 8 all over again when you get to Cal 2. Depending on what teacher you have, they might go slow and start from the beginning, or they might say, oh, well, you had pre-cal, you should already know the first 5 sections, okay? So it just depends on who you've had before or who you have for calculus. I like to start from the beginning just to make sure we're all on the same page and then go from there. But if you have another instructor for Cal 2, they may just say, oh, well, you should already know a little bit about vectors, okay? There are two kinds of products in vectors. There's what's called the dot product, which is the one we're gonna learn in this class. And then when you get to Cal 2, there's another one called the cross product, okay? The cross product is used widely by engineers. So if you are an engineer, you will see the cross product in the future and you'll see it a lot, okay? For us though, we're only gonna be concentrating on the dot product, okay? And I just wanted to point that out because someone might say, well, why do you say dot product and not just product? And it's because there's two different kinds, okay? So basically 2 different kinds of multiplications that you can do. The difference is with a dot product, when you're done, you end up with a scalar, meaning you end up with just a normal regular number, okay? So you multiply 2 vectors together and you end up with a regular number. With the cross product, you multiply 2 vectors together and you get another vector, okay? So there's a huge difference between the 2 kinds of products. So for the dot product, it's very simple. You basically take the first components and multiply them together. And then you take the second components and multiply them together. And then all you do is just add those results, okay? So mechanically, there's not a whole lot going on in this section. We just have to do it all, okay? And then there's some properties of dot products. Notice that because multiplication is commutative, meaning I don't have to write in this order, I could switch them, right? Because they're commutative, so is the dot product, okay? So it doesn't matter which vector's in the front or which is in the back, you'll get the same answer when you do the dot product. Because eventually you're just gonna have to add it all together anyway, right? Then if you multiply everybody by 0, of course, you're gonna get 0, right? And then here they have some distributive properties. So there's 2, this is one of the distributive properties. You can have U and then the dot of a sum. And you basically are gonna take the dot with this guy, and then you're also gonna take the dot with that guy and put a plus in the middle, okay? So notice how they did U dot V and then they did U dot W. Okay, this is kind of like your distributive property. And then this is like squaring it. But if you're going to be multiplying the term times itself, you're essentially finding the magnitude squared. That one's just like an observation somebody noticed. Now here, you have to be careful because this is not a sum, right? This is a product in the middle. Now we have an associative property. The associative property says you can, instead of multiplying these guys together, you can basically group those two together. And if I do that, then I have that constant, whatever that constant was, times just the U, okay? And then the V's over here by itself, and I'll have to do the dot product with that. Because this is a product. This is not a plus or a minus. When you have a plus or a minus, that's when you distribute or FOIL. So it's different. And then they also notice, again, because multiplication is commutative, it really doesn't matter whether you multiply the U by that constant or you multiply the V by that constant, you're still going to get the same answer. I don't ever use this or this, but they're observations that somebody made, okay? I guess after doing 10 million of them, they're like, hey, wait a minute. It didn't matter if I did it this way or this way, okay? So let's go to our problems. And it wants us to find the dot product of all three of these. Okay, so for part A, if I work out my solutions, I have to take the first component 4 times the first component 2, and then add the second component of the first guy times the second component of the second guy. This is literally all we're doing. Okay, so I get 8 plus 15, which is a whopping, what, 23? And that's the scalar answer that I get. It's just a regular real number. You'll see the applications of this stuff in a minute when we get there. Because you're like, why do I need to do this? So for B, these are my vectors. And if I want to multiply those, I'm going to take the first components and multiply them together. And then I'm going to take the second components and multiply them together and add the results. So I get 2 plus a -2, so I get 0 here. Just coincidental that I get 0. So then for this one, I'm going to have the first component 0 times the first component 4 plus 3 times the -2. I get 0 plus -6, which is -6 for that dot product. Not too bad for this one. Now let's see what they want. So now they gave us 3 of them, and I think I stapled this in a bad position. I'm gonna undo mine. You don't have to undo yours, so I can see what it is. Okay. So W is apparently 1 and -2. You don't need to undo your staple. I just wrote it over here. Okay, so they want us to find 3 different computations. So we're gonna go for it. Let's see what we get. So first for part A, I'm gonna do U. I'm gonna draw this big parentheses, and then I'm gonna have U dot with V. Close that big parentheses, and then there should be another dot there. That was my error. No, there should not be a dot there. My error this time. And the VW is 1 and -2. So let's do the parentheses and figure out what this dot product is. So I get -2 plus -12, which is -14. And then how do you multiply a scalar times a vector? You just multiply that scalar to each component of the vector. So I get -14 and then +28. That was one of the definitions at the beginning of 8.3. Now for B, we have U dot with 2V. So we do need to do our scalar multiplication before you can do the vector and the multiplication. So I do actually have to figure this out first before I can do that dot product. So I'm just going to distribute that just like I did with the -14. So this becomes 4 and -8. And then now I can do my dot product. So I have -4 plus a -24. I end up with a regular number, -28. And then C just asked me for the magnitude of U. So that's the old school definition. It's the square root of the first component squared plus the second component squared. And so we get the square root of 10. That one has nothing to do with the dot product at all. Okay, so why do we need to know about dot products? When do they come in handy? This is one of the first things that we need to know about dot products. Okay, there's really two things, three. There's like three things we're going to use dot products for. And it may not make a lot of sense right now. Right now, we're just doing the mechanics of it. But when you get to Cal 2, you're going to want to remember this stuff. And you still have something in your notebooks to remind you later. So the angle between two vectors, actually, you can use a formula here. So this is the angle between two vectors. This is not the angle of a single vector. This is the angle between two vectors. So there's a difference between this being my U and figuring out that angle, and this being my V and then figuring out this angle. Okay. So in order to find out that angle, you do the tan inverse of the the y coordinate over the x coordinate, right? We already know how to find the angle of U. And I even know how to find the angle of V. Tan inverse of his y coordinate over his x coordinate. But if I want to find the angle in between these two guys, there's no formula so far. Okay. But now there is. Now that we've talked about the dot product and introduced that, this is the formula to find this angle. Okay. So all you have to do to get this angle right here is to do the cosine inverse of the dot product between the two angles and then the regular product of the two magnitudes. Okay, so I didn't want to put a dot in there because I didn't want it to look like it was the dot product, but it's literally this number times this number. Okay, so let's go compute that for one of these problems, like in example 3. So it says find this angle. So I'm just going to rewrite this formula, but instead of writing the U's and the V's, I'm going to put what U and V is. So it's 4, 3 dot product with 3, 5. And then at the bottom, I have to find the magnitude of 4, 3. And then I have to find the magnitude of 3, 5. And so for the dot product, let's see, we're gonna do 4 times 3 plus 3 times 5. For the bottom, I have to do the square root of 4 squared plus 3 squared, and then the square root of 3 squared plus 5 squared. So here I'm gonna get 12 plus 15. And in here, I'm gonna get the square root of what? 16 plus 9 is 25. And then 9 plus 25 is 36. No, 34. Is that right? Okay, not too bad, not too bad. Now, this is obviously not a nice number, so I'm not gonna bother trying to work any more in there. Let's see, 12 plus 15. What is going on? 12 plus 15. Square root of 25 is just 5, but I don't know about that guy. He doesn't have a nice square root. And when I take the cosine inverse, I get approximately 22.166 degrees. Well, the sign will tell you how much to round it, but I don't know. So I'm just gonna leave it at 3 decimal places. But normally it'll tell you to the nearest degree or 2 decimal places or whatever. But we did find that angle. Okay. The next cool thing that a dot product tells me is whether or not 2 vectors are actually perpendicular to each other. What does perpendicular mean? Perpendicular means is if there's a 90-degree angle between U and V. Okay. It just so happens that if there is a 90-degree angle between U and V, and it doesn't matter how U and V are positioned. If this is U and this is V, there might still be a 90-degree angle in between them, right? Does not matter how those guys are rotated. To know whether or not there's a 90-degree angle in between them, the dot product would have to come out to equal 0. Okay, so that's one quick way to decide whether or not they are in fact perpendicular. In the vector world, though, they don't call them perpendicular, they call them orthogonal. Like we need more words, but for the same things, but that's what they call it, okay? So if you see that word orthogonal, just know that it just means perpendicular, and perpendicular means there's a 90-degree angle between them, okay? So they're essentially asking you, tell me whether or not these 2 guys have a 90-degree angle between them, okay? And so I can't figure that out just by doing the dot product. So the question is U dot V equal to 0? If the answer is yes, then that means they're orthogonal. If the answer is no, then they are not orthogonal. Okay. If I find that dot product, let's go see if it is 0. That's the question. So 2 times 6 plus -3 times 4. Does that equal 0? I think it does, because I get 12 and -12. And don't those equal 0? They do, right? So that means U and V are orthogonal. Had gotten anything else other than 0, then the answer is no. Okay, no, they're not orthogonal. You have to get 0 in order for them to have that 90-degree angle. Now, again, this might seem like a bunch of nonsense, but it literally is busy work for us for right now, okay? When you get to Cal 2, you will actually in Cal 3 as well, you will have to do this a lot. You will have to, what they call decompose a vector. So you basically turn one vector into the addition of two vectors, okay? It's not as easy as just subtracting. There's a little bit that goes on in that, okay? So it says for vector components. So it says, let U be the non-zero vectors such that U can be written as some vector plus another vector, okay? Where the first vector and the second vector are orthogonal to each other, okay? So essentially you're turning this vector into two vectors, and those two vectors have a relationship, and that's that they're orthogonal to each other, okay? However, this guy is going to be parallel to the V vector, okay? And if you remember from the beginning of 8.3, in order for something to be parallel, it basically just has to be a constant multiplier of another vector, okay? Now, the vectors W1 and W2 are called the vector components of U. The vector U1 is called the projection of U onto V, okay? And is denoted by this little notation. Okay, so it's the projection of U. You can put parentheses here for the word of, but the projection of U onto V. Okay, this is the way they write it. The W2 vector is basically, you do take this and you just subtract the W1 over. If I subtract the W1 over, then I can figure out what W2 is by taking U minus that W1. But how the heck do I figure out what W1 is? They're giving you the formula right here. W1 is that projection one, right? And W1 has this formula here. So if you want to figure out the first component vector, you have to use this formula. If you want to find out the second component of the vector, then you just subtract the first component, okay? Again, it's a lot of words, a lot of stuff. We're going to work one out, okay? So let's see. I need to write that formula down because I do forget that one. V squared and then V. I think that's right. Yes. Okay, good. Okay. And pay special attention to which letter is where, because if they for some reason ask you for the projection of V onto U and they switch these variables, you need to switch them over here as well. I don't think they do that to us, but just in case, especially in Cal 2. I know they like to do it every which way in Cal 2. So it says find the projection of U onto V, then write U as the sum of orthogonal perpendicular vectors, one of which is the projection of U. So essentially what they're doing is they're asking me to write U as W1 plus W2. They want to know these two components. W1 can be found by that formula, okay? And if you want to find W2, all you have to do is use subtraction. So here goes for the W1. I'm going to take U, which is 3, -5, and dot product it with V, which is 6, 2. Then at the bottom, I'm going to do the magnitude of V squared. So the magnitude of V is to take the first component of V squared plus the second component of V squared. And then I'm going to multiply this by the V vector. Let's see what we get here. So this guy times this guy will give me 18. And this guy times this guy will give me a -10. 36 plus 4 is 40, but it's going to get squared, isn't it? So then up top, I have 8, and at the bottom, I just have 40. that can reduce to 1/5. And if I distribute the 1/5, I get 6/5 and 2/5. So this is W1. If I want to find W2, I'm going to take U minus W1. And so what was U? U was 3 and -5. And W1 is this fractions. So I'm going to be doing 3 minus 6/5 and then -5 minus 2/5. 3 minus 6/5. And I get 9/5. And then here I get -27/5. Yes, -27/5. So that's W2. So if they want you to write U as the sum of those two vectors, U is going to be this guy plus this guy. Okay. And if I were to add these two together, I would get 15/5, which is 3. And if I were to add these two together, I'd get -25/5, which is -5. Okay. We have 2 more and then we're done. Hopefully we have time for the last one. So here it says a 200-pound cart is on a ramp inclined at 30 degrees, and it wants to know what force is required to keep the cart from rolling down the ramp. It says, hint, your angle there is a unit vector. So this guy here is a unit vector. These are all my old pages here. Okay, and then it says that U1 is this way. So if I want to find F, we're going to need to find W1. But that means I need to know U and I need to know V. So I know that U, if it's 200 pounds, how much force is going down this way? I know that this measurement is going to be 200 pounds because that's pulling down all the way the weight. The weight has gravity, right? Gravity goes downward toward the ground. So that's going to be my 200 pounds. Let me wait on this one. This is in 8.4. I feel like my little diagram is missing something. So I'm gonna go see if they have one in here. They do not even have one like this in here. Well, then fine, I'm not doing it. Nope, it's just a bunch of dot products and finding the angles and then telling me whether they're orthogonal or not. There's one with the projection, and then you have to find the second vector. How do you find the second vector? You just subtract whatever you get for this one from you, right? That's how you get the second vector. Okay, determine the work. Okay, so you have two that do actually want you to determine the work. So I'm gonna skip this example just because I don't see anything in there that's gonna pertain to you. So we're gonna skip example 6. I do have work on the next page. So we definitely need to talk about the work. So for the definition of work, we have that work can be determined by the projection, the magnitude of the projection times the vector. Another way of writing that, if you want to use U's and V's, is the projection of U onto V times V. Okay, that's the other way of writing it. It's basically the magnitude of the W1 times the V. Okay. And then over here, you're just taking F, which is the U dot the V. So there's two different formulas there. Okay. You can choose which one. And I think I already wrote this one down, but this one's silly. Okay. So it says determine the work done by a person lifting 295 newtons bag of sugar 9 meters. Okay. So you have to remember that your force, I just wrote the answer. But your force is going to be this one here. And if I'm lifting, I am not moving left or right. I am only moving up 295 newtons. And then for the bag of sugar, it is going to be moved. And normally when you're moving, you move toward the right, the positive direction. So I will be moving it 9 meters toward the right, but I will not be moving it up or down. See, but then that doesn't work, right? Because what happens when you do this dot product? What do you get? You get 0. So now I understand why they're using that formula. Do you have a problem like that in here? You do have one like that in here. So you are gonna have to do both of them. So even though this one looks a lot like number 24, so apparently for 24, all you have to do is 265 times 3. And that one's easy. I get 795. That one's easy. This one, though, you actually have to do some computation for it. Okay. So I actually want to do a number like number 3. So this is 8.4, number 23. P is this. Q is this. And then it says V is, and I'm going to write it in its component form, -8 and +8. So I just picked that data, right? P was this point, Q is this point, and then the V, I put it in the component form instead of the IJ form. So basically, I have to figure this out, okay? So if I want to figure that out, I need to figure out what the projection is. First of all, let me figure out what the world PQ is. That's going to be -3 minus 1, 9 minus 2, which is -4 and 7. So that's what PQ looks like. And if I want to find the projection, I have to use that formula. So projection of PQ is going to be this guy dot product with this guy. And actually that's wrong. I want to show you where my brain is at, okay? This is the formula, right? Notice what vector is here and what vector is there, because where they go in that formula matters. Notice that I have PQ as my subscript. So everywhere I see a V in this formula, it's actually turned into a PQ. And everywhere I had a U, it's going to turn into a V. So this is actually going to be the V vector dot with the PQ vector over the magnitude of the PQ vector squared, and then multiplied by the PQ vector. So I'm just replacing the values with the values that I have over here. Okay. They switched it on me. They had called this one U before, and now they're calling it V. Okay. So it's the only thing that's different on this problem. I knew they were going to do that. I was trying to mention it earlier, but I was like, maybe not, but it happened. So let's see what we get. We get -8 and 8 dot product with our -4, 7 over the magnitude -4 squared, 7 squared, and that whole thing squared. And then dot with our, or just multiplied by that PQ vector again. So this times this is 32. This times this is 56. And then I get the square root of 16 plus 49. I get 65. And so then we have 32 plus 56. That's 88. The square root and the square go away. And so then if I multiply 88 over 65 times -4, I get -352 over 65. And if I do 88 over 65 times 7, I get 616 over 65. So that's the projection of P, Q, and V. However, that's not the answer for the work, because the work is the magnitude of that projection times the magnitude of just PQ. So that means I need to be doing the magnitude of this vector, this ugly vector, times the magnitude of PQ. And PQ is this vector. So let's go figure out what those magnitudes are. So I'm gonna have a square root and a square root. So this guy squared plus this guy squared, this guy squared plus this guy squared. I have no idea what this is gonna be. Let's see. Parentheses 352 65 squared plus parentheses 616 divided by 65 squared, and then the square root of that. Oh, no. I think when we did these, we got 16 and 49, which was 65. So 7744. That's just what the calculator told me. I don't know how that is. I'm guessing this has a fraction over 65. And then the square root of that is 88. So be very careful when you're doing number 23 on your homework. Make sure you're using this formula for the projection. Okay, make sure you use that formula. Okie dokie. That is it for these two sections. We are going to go into 8.5 and 8.6 the next class. Those two sections are a lot different than these vector things. We're going to talk a tiny bit about the vectors, but we're going to get into something, the complex plane. So you're going to see all this vector stuff being applied to imaginary things. If that makes anything any nicer, right? but we'll see it. And then once we get to that review, it'll really help us to like hone in on what we got to concentrate on for that test. Okay. So one more lecture and then one lecture for review, and then we'll have the test. We'll have the test. I don't think it's for a while though now. So let me go to my modules. I think this one is not for a while. So see, we still have Thursday's lecture, and then the following week we will have review, then homework, and then it looks like you take that test before the break, before the Thanksgiving break. So after Thanksgiving, you have nothing to worry about. It's already all done, right? Chill out, eat all your turkey. When we come back, we'll start preparing for the final. Okay, make sense? That's it then. You guys have a great day. I will see you, I hope, on Thursday.